Welcome to the channel EC TechNest. Today, the 15th day of the 100-day series of digital design and Verilog series. Today, we're going to talk about flip-flops. Flip-flops are basically bistable elements in sequential circuits. It means they can hold two states, that is 0 and 1. And first, we'll talk about SR flip-flop. It is called a set and reset flip-flop. It is the simplest type of flip-flop. This is the operation. If S is 1 and R is 0, sets the output Q to 1. If S is 0 and R is 1, resets the output Q to 0. If S is 0 and R is equal to 0, it will hold the previous state. If S is equal to 1 and R equals 1, it enters a race round condition, that is invalid state. This is a truth table. See, when 0 and 0 is there, we will hold the previous state. That means no change. If 0 and 1 is there, you will set reset state, and if it's 1 0 will set state, and 1 1 is indeterminate. It means it is an invalid state. This is a circuit diagram of the SR flip-flop. So this is how you write the Verilog code for an SR flip-flop. You have the four inputs, that is S, R, reset and clock. Output reg is Q. Always at positive edge of the clock, you'll check. I mean, if reset is equal to 1, Q will be 0. That means you will go back to the base state, that is 0 state. Else you will begin the case condition on S and R. Based on the values of S and R, you will get the output. If it is 0 0, you will hold on to the previous state. If it is 0 1, you will reset. 1 0 set. 1 1, it is an invalid state. Then you will get an end case and end module. The D flip-flop. The D flip-flop is a very common type of flip-flop. It's also called as delay flip-flop or data flip-flop. It is essentially an SR flip-flop itself, just with an addition of an inverter. Whenever whatever value is present at the D input during the clock edge, it is captured and transferred to the output Q. It effectively delays the input clock by one cycle. So it is called as a delay flip-flop. See the truth table. Whenever the input is 0, right, it will hold on to the previous state. If it is 1, it will again hold on to the it will hold the same thing. Whatever is in D will put to the Q. We'll see the logic circuit. In SR flip-flop, you had here S input and here R input. What we are changing is we are adding a NOT gate. What they have given here? Yeah, we'll be using an inverter. Then we have module D flip-flop. Here, there is one mistake. I don't know why it is given as an XOR gate. Please see to that it's a NOT gate. We need to put a NOT gate, not a. This is like it's an OR gate actually, not even an XOR. It's an OR gate. You need to put a NOT gate, not this one. Okay. Please change this to a NOT gate. Then we have the Verilog code for a module D flip-flop. You have three inputs: your clock, reset, and D. Output reg is Q. You will see that if it is a reset, your Q will be 0, or else Q is nothing but whatever is your input D, that will be the Q. I hope you can understand this through the truth table. Whenever input D is 0, output is 0. Whenever it is 1, it will be 1. So why do we use this circuit? Main thing is, if you want to create a delay, adds a delay by one clock cycle, you will use a delay flip-flop. That's it. Nothing much more to this. Or it can also act as a storage element for a short period of time. JK flip-flop. The JK flip-flop is an improvement over the SF flip-flop. It eliminates the invalid state. Let us see what it will do. It has J equals 1, K equals 0. It will set Q to 1. And J is 0 and K equal to 1. It will set resets to 0. J is 0, K is 0. It will hold the previous state. Here, it enters a toggle state. J is equal to 1, K equals 1. So, the output switches to its complement. If it was 0, it becomes 1. If it is 1, it becomes 0. So, as we discussed in the JK latch, again, this leads to race around condition. Again, it will keep on repeating. So, to solve this problem, we introduce the master slave JK flip-flop. After the T flip-flop, we'll discuss about master JK flip-flop. See the logic circuit. You are giving clock pulse. Here you have an AND gate with input J and K. This is how you will get the logic circuit diagram for JK flip-flop. Whenever J is 0 and K is 0, you will get the previous state as output, that is Q0 or Q0. You will have no changes. Whatever was in the previous state, same will be repeated here. If J is 1 and K is 0, your output will be 1. That is, it will be set. 0 and 1, it is 0. It will reset. 1 and 1, it will toggle. Now we went in the SR, we had the problem of invalid state. Here we have the problem of toggling. That means it will keep on continuing. It is shifting between 0 to 1, 1 to 0, 0 to 1, 1 to 0. For that, we need to solve it, right? Let us see how T flip-flop can solve it. We'll check whether it can solve it. The T flip-flop is a simplified version of the JK flip-flop where J and K are the inputs tied together. Okay, here we are not able to solve it to that extent. What we are doing is we are just shorting the J and K. What we did in D was we added an inverter for SR flip-flop. Here we are just shorting it. Means both the inputs will be T itself. Here T equals 0 is hold state. The output remains the same. T equals 1, it will get toggled. We'll see the truth table. Whenever the input is 0, right, it will hold on to the previous state. Whenever it is 1, whatever is the previous state, it will toggle it. If the previous state is 0, your output will be 1. If the previous state is 1, your output will be 0. So simple to say, when it is 0, hold on to the previous state. When it is 1, toggle the previous state. Simple. T flip-flop. You have 3 inputs, clock, reset and T. Output edge is Q. Always at the positive edge of the clock, our this program will start running. If reset is 1, you will Q will become 0. Output is 0. Else begin. If T, it means if T is equal to 1, you will toggle. Q will become inversion of the previous state. Else Q will be the same as previous state. That means if it is 1, toggle it. If it is 0, keep the previous state. Simple. Then we have the master JK flip-flop, master slave JK flip-flop. We use this to solve the race around condition. What is race around condition? As we discussed before, when J is equal to 1, K is equal to 1 and the clock pulse is too long, the output can toggle multiple times. See, if this J equals to 1 is continuing for a very long time, consider 2 nanoseconds, 3 nanoseconds, by that time it would have toggled multiple times. So we need to stop this. So that is how this master slave JK flip-flop has come into picture. The master slave configuration fixes this by separating the sampling of the inputs from the updating of outputs. What we have done here, instead of keeping two JK flip-flop separately, what we'll do is we'll have one master JK flip-flop and one slave JK flip-flop. The difference here will be whatever was the output of the master JK flip-flop will be given as input to the slave JK flip-flop. The other thing that changes is the clock. Here, whatever clock you are giving, you will give it as an inversion to the slave flip-flop. So if you are giving clock as 1 here, the slave will be getting clock as 0. That is what you have discussed here. Principles of operation. The circuit operates in two distinct phases based on the clock signal. Phase 1, clock is high, then clock is low. So this is phase 1, this is phase 2. Clock is high, here clock is low. Then it will change. Let us see. The master is active. In this case, first the master is active. So it will respond to this JK input, whatever you are giving here. It decides what's the next state should be. The slave is disabled because the inverted clock is 0. So if your clock is 1, master is enabled, slave is disabled. The final output Q remains unchanged during this phase. So what is happening, because of this, your whatever problem you had with the toggling is stopped. So when clock is low, the master is now disabled. So changes to J and K will no longer affect it. It means since this setup is only disabled, here whatever the output is there, no, it will not affect this slave flip-flop. Here whatever this is, it will become 0 and your outputs also will be 0. So you can start this as a fresh flip-flop. The slave becomes active because clock is now 1. The slave simply copies the state that the master captured in phase 1. So whatever was the output that was in the master flip flop will be copied to the slave flip flop, and that will be your final output K. The output Q only updates once per clock cycle on the falling edge, effectively eliminating the race around condition. So since this setup is itself acting just like a storage element, you should understand that whatever output we got, it is just copying it and pasting it as output. So it is solving the JK whatever toggling we had, no? So that race around condition is getting solved here. Here we learn how to write a Verilog code for this. So as we discussed in the JK flip-flop, we have written the same code here. Input is JK, clock and reset. Output is Q. So when it is 0, 0, you will get Q, the previous state. 0, 1, it will be reset. 1, 0, you will set. And 1, 1, you will toggle it. This is your basic JK flip-flop. Now if I want to create a, what do I call it? Master slave JK flip-flop. Here you will have the same number of inputs and outputs. Extra will be Q bar. Here also we could have written a Q bar, but we haven't written because yeah, here only I have given the negation and I have not mentioned about Q bar here. But for master slave, I mentioned it. You'll have two wires, that is wire MQ and wire inverter clock. Okay. So whatever the output of master is there, no, this one. This one I have named it as MQ, and this wire, whatever is the output of the first clock which is coming, that is your inverter clock. So now what I'll do is I'll tell that assign inverter clock is negative of clock, whatever you had given. So inverter clock is just negative of the clock. So it is inverting. Now I have to instantiate whatever JK behavioral. I'll tell that it is a master instance and I'll connect it. First when I connect it, I'll connect JK clock reset and whatever is output will be given to MQ. Here what happens is for the JK behavioral slave instantiation, J will get a proper MQ, but K has to be given with a complement. And we see that the slave is getting an inverted clock. This clock is given as input to the slave flip flop. Then reset in the final output, and your Q bar will be negation of Q. That is how you will write this master slave behavioral implementation of Verilog code. Whatever you have written here, you are just taking it an instantiation. Just the two changes will be creating this wire inverted clock and assign inverted clock, and here again the negation part. This you have to remember. If you have any doubts, feel free to put it down in the comment section. Thank you.